It's Sunday, June 26th, 1994. A new insight into the difference between tendency and probability. When looking at holistic systems, we would be looking at two concepts. Either a series of points that are connected by some kind of relationship or glue, as it were, or a series of foci in which like gravitational fields, a number of points exist at which gravitation is at a max, but not one single point. Many points spread about, and their influence is felt to some degree holistically all the way across the space in between. These two views of gravitational pools that focus at a particular point or have their greatest intensity at a particular point and then spread out in all directions, influencing with their ripples, as it were, all the way to the edges of the closed system, as opposed to a number of individual points that do not influence anything at all by their existence and are merely connected by some kind of relationship or process at work that involves both of them. These two views are both present. The particulate view, which would look at, for example, in astrophysics, the planets, asteroids, every speck of material as being something that that exerts an influence on other pieces. An influence in terms of if one smashes into another, it can transmit some of its energy to the other one, which would then continue barreling off through space and smash into something else. When we look at the aspect of interconnectedness in a holistic closed system, such as astrophysics, we would find the particulate or spatial way of appreciating it would look at the billiard ball effect of one thing ramming into another in transferring force, which is a vector containing both direction and degree. So vector science is going to be a particulate appreciation. However, the appreciation of the gravitational wells, as they were, the gravitational pools that exist within the universe, those are the tendency appreciation. Now, what's the difference between tendency and probability in relationship to this? In terms of probability, we are looking at items that are particulate in nature, defined, spatial, points, vectors. And we're saying that each one of these particular points, some of them will have an effect and some of them won't, meaning that it's a binary situation that exists, a digital situation, in which something is either a 0 or a 1, and we can say that a close call doesn't mean anything. The old expression, close is only good enough in horseshoes, is equally applied to astrophysics when you're looking at a particulate or vector view, a spatial view. At that point, what is close has absolutely no effect, because even if an asteroid comes within fractions of an inch of another asteroid, but they do not actually touch, there's going to be no interaction at the vector or particulate level, because no energy will be transmitted by that means, via direct contact. In other words, it's still a 0 until it touches, and then it's a 1. Now, the difference between the two, what bridges the gap between a 0 and a 1? How can we say that something is closer and ever closer and ever closer? Because there's a second force at work, which is the tendency part of it. Rather than saying that here's a particulate view dealing with vectors and absolutely touching one piece to another, as in billiard playing, we look at gravitational fields much more like magnets, where you can say that the closer two magnets get to each other, the more of an influence they'll have on each other without actually touching. Now, the key to all this is that both forces are at work at the same time. Now, the error in the way Einstein was looking at relativity was that he was combining the two and saying that they are intrinsically connected. In other words, whenever you see an item of mass in the universe, it is producing a gravitational field that is warping space, and that's the second part of the same force. In other words, there is a single event that occurs, which is the existence of an item, and by existing, it warps space, creating this gravitational force. That's a very causal relationship. Even if you look at it as being non-causal, more holistic in saying the two exist simultaneously, they're still connected insofar as Einstein's theory would allow. This is because he's looking at the universe from an inside perspective, a subjective view in which only three things are possible. You look at energy, you look at mass, and you look at space-time. You cannot see space and time as being independent. This is the same problem we have when we look at the speed of light as being a constant. It's only a constant because the two aspects of the speed of light, speed being both space crossed and the time that it takes to cross it, those two items are held together, bonded together, locked together as a view, saying that when one goes up, the other one goes down, and in direct proportion, meaning that it appears to be a constant. In fact, it's really wavelength versus frequency. The wavelength of light times the frequency of light. Frequency is an estimation of speed based on time. It says how often you see a complete cycle, whereas wavelength is an estimation of speed based on space, where you're saying how long is a cycle. So because space and time are bonded together in space-time in Einstein's relativity, we end up unable to separate them, which then results naturally in the assumption that any particle that exists in nature will be associated with a specific gravitational effect that is intrinsic to that item. But it's really not intrinsic. When we look at the difference in mental relativity between probability and tendency theory, in tendency, again, we're going to say, here's the gravitational part of the argument. The gravitational part says that when two asteroids pass close to each other, even if they're on opposite sides of the universe, they're going to be having an impact because of their gravitational effect, which is holistic and predicted by mental relativity, is not something that exists as waves that ripple out, at least not from a spatial perspective. From a spatial perspective, it's only going to be perceived as a force that is synchronously applied all throughout the universe. In other words, it doesn't take any amount of time for a gravity from a particle that comes into existence out of energy. For example, if we were to create fusion and create a particle that's heavier than the particle that existed before, when we do that, that new particle, that extra mass that has been added at a particular point in space, is immediately going to have an impact on the far side of the universe. It doesn't take a billion years to get over there. It seems instantaneous from a spatial perspective. In reality, if we look at it from a temporal perspective, we're going to see that that particular effect does appear as waves, but only waves in terms of time, in terms of frequency, not in terms of wavelength, not in terms of space. So when these two asteroids pass in space, even if they don't connect directly and have a vector impact or spatial impact on each other, they do have a gravitational impact, and that occurs all the time, not just when they get close. It accentuates when they get close. And if we look at the mathematical curve of this particular relationship, we're going to see that as they approach each other, the greatest distance is passed between them with no appreciable increase. It's very, very small. But we end up with a hyperbolic approach of a limit line when we get in closer proximity. And in fact, it gets to the point where the gravitational effect between the two particles reaches the point that when they actually connect and touch each other, they become a single particle as far as the gravitational field. The fields merge because they can no longer be identified as separate. That's the magic moment when it switches over from a gravitational effect in a temporal universe to a vector effect or linear effect in a spatial universe. In other words, there's no effect at all, zero effect of transmitting force from one particle to another as long as they are separate. But as long as they are separate, there are separate gravitational effects they have upon each other in a sense of holism, a synchronous holism. As soon as they get close enough that that limit line is being approached and they actually touch each other, then the limit line has been breached. They are now on the other side, and essentially there's a straight line coming down the middle, and from the left moving towards the middle is a hyperbolic curve approaching that limit line, that vertical limit line, from one particle. On the other side, coming from the right towards the center, is a gravitational effect approaching that limit line from the other side. And when the two actually touch, then at that point they actually reach the limit line. It becomes a straight line instead of a hyperbolic curve. And it describes then, instead of a gravitational relationship between the two, there is a particulate relationship between the two, dealing with the transfer of energy or power from one to the other, a vector transfer. So the two exist simultaneously in terms of their potential, but in terms of their actuality, only one of them can exist at a time. And it's the switching back and forth between the temporal and spatial perspectives, between the tendency and the probability that creates the flip of the binary switch, going from spectral appreciation to analog appreciation. Now, in terms of probability and tendency and the more common usage of looking at likelihood, again, blends two concepts. And these two concepts that we're talking about are, when you say, what's the probability of any given of a given interaction between a number of pieces and a number of other pieces, you're saying that some will be interacting and some won't be interacting. In other words, it's definitely a binary situation, a 0 or a 1. You're going to say out of 100 pieces, 85 will be in a particular state. Well, that's a probability. It's saying it doesn't matter which one, 85 will be in that state, and the other 15 out of the 100 will not be in that state. And because of that, you're saying essentially those 15 are not participants because they are not in the state that you're desired. They may be zeros. And the ones would all be the 85% probability. That would be a way of looking at those that actually are going to interact. But there is no specificity as to which ones will interact and which ones won't. In fact, it really doesn't matter. That appears to be the realm of chaos in a vector appreciation of things, is that we can't tell which ones will interact and which ones won't interact, and that's one way of looking at likelihood. But there's a second way of looking at likelihood, which is the temporal perspective. And in terms of that, dealing with tendency theory, we're saying that each one of these items has perhaps an 85% of its force is attractive to something and 15% of its force is repulsive to something, meaning that overall there is a tendency to try to become part of that one state out of the zero state that is 85 compared to 15 factors of force that are repelling or against transmuting its state. That is a little different view, because instead of saying that everything is either a 0 or a 1, this says everything has a tendency to be a 1 85% of the time, as it were. So looking at that view, we can say that every single particle out there has a tendency towards something and a tendency away from something, and that if you say the tendency of these items can be grouped as having the same tendency, then they can be classified as the same thing. If they have different tendencies, they are not the same thing. So likelihood and chaos, in a temporal sense, have to move into a different place to hide, because we're illuminating a different area by looking at this particular appreciation of likelihood. In other words, we can't just say that chaos is which ones will do what, because that is the spatial view. In this one, chaos is, for this particular one, will it or won't it? And so we move down to looking at the particulate nature, because we're looking at the relationship of tendency, the gravitational field among all of them. Whereas when we look at the particulate view of the holism, then we're going to look at the temporal sense of how many within a given amount of time are going to be in one state or another at any given point in time. So, in other words, when we take a temporal view, we end up with spatial chaos. When we take a spatial view, we end up with temporal chaos. Now, that leads us right back to the relativity again, meaning that in order to fully understand what's going on in astrophysics, we have to look at wavelength and frequency as separate, and we have to realize that the frequency can change without affecting the wavelength. And for the frequency to change without affecting the wavelength requires that the speed of light not be a constant. Now, the only way the speed of light cannot be a constant is if we separate the spatial and the temporal sides and say that energy and mass are also involved, so that when we are looking at energy and mass in relationship to space and time, when time goes up, if space does not change to go down, then the compensation must be made up elsewhere in terms of energy and mass. In other words, energy and mass do not merely transmute one to another, as Einstein said, with the speed of light being a constant, but in fact, time, space, mass, and energy all transmute between each other, but we're only going to be able to observe two of them because we're standing on the other two to measure that when we're looking at the universe from the inside. Because of the way our species is made up, we share a commonality of being able to look at space-time as our measuring stick and watch what happens to energy and mass measured against space-time. Therefore, we're going to see changes in energy and mass, and we're not going to be able to watch the differing relationship between space and time because one goes up and the other one appears to go down. They appear to be locked on a teeter-totter, and there is no way that both can go up or both can go down. When we look at the dynamic pairs in mental relativity, however, we can have a pair, three different kinds of pairs. One pair in which when one goes up, the other goes down, which is the traditional view, and that is indeed the dynamic pair relationship. Then there's the companion pair relationship in which when one goes up, the other one goes up with it, or that's dependent pair relationship. When one goes up, the other goes up with it. When one goes down, the other one goes down with it. In other words, they're locked in a scale where they both move in the same direction. And then there's the dependent pair relationship where when one goes up, the other one